Good evening, my 11th standard warriors. Welcome to the first lecture of Oscillations, where we are going to talk about simple harmonic motion. Hi Saja, Gokulnath, Harita, Ramya, Dakshin, Aishwarya, Suchimama, welcome aboard. This is Shreyas here, your physics master teacher, going live at Vedantu on your favorite channel, JEE Enthuse. Now, you are watching the Nurture series. So what is Nurture series? It's a long-term course, free of cost, on YouTube, just for you. And we started back, long time, and we have completed so many chapters like rotation, center of mass, and now we are on simple harmonic motion. And today is lecture number 1. Let me tell you what we are going to do, and we are going to cover this chapter in detail. So, what are we going to start with? We're going to start with what is periodic motion, what is oscillations. Then we will talk about the different terms and the equation of simple harmonic motion. The terms like frequency, angular frequency, amplitude, and phase, and what are these things? How do you find velocity and acceleration? All of that will be dealt today, and you will see that there is a lot of interesting mathematics that blends perfectly well with the physics out here. And you are going to end the class with differential equation and a spring mass system which oscillates. That will lay our foundation for the lecture number 2 of oscillation. So welcome aboard, and my name is Shreyas. I am teaching kids for almost like a decade now, and I am here to spread the joy of learning to all the nooks and corners of the country and even beyond the borders. Hello Ishpreet, thank you very much for all the hearts, lovely bacha log. Hi Silwai Panyam, welcome. Thank you Aishwarya. Hi Tanuja. Hi KSK, Ashika. How are you? Are you all excited to start the new chapter? Was the last chapter a little bit tough? Do you want more sessions for problem solving? Please let me know in the comment section. And I hope you have also done your homework. I'm going to give you homework questions and we're going to read the names in the next class. So make sure that whatever homework I give you towards the end, you solve it so that your name will pop up in the next class. Welcome aboard. Does this chapter require any prerequisites? Yes, you need to know basics of derivatives, you need to know sine, cosine functions, and you need to know obviously Newton's laws of motion. That's what you need to know, and obviously basic kinematics. All right. Oh yes, Remo. Okay, don't worry KSK, we'll have a separate session again on rotational motion as well. I'm very good, Shanu. And Bala, hello, welcome aboard. So Harshil is super excited. Harshil, I'm seeing you for a very long time. I used to see your comments. Alright, so let's begin with the class, and thank you so much for liking the video. And well, in case you have forgotten to subscribe the video, to our channel, please do that right away, because a lot of lectures coming ahead and you do not want to miss all the important announcements. You don't want to miss KVPY sessions. You don't want to miss any important sessions specially designed for you. So I hope you have hit the subscribe button too. So let's start with periodic motion. Vanakkam everyone, vanakkam. Look at this beautiful earth rotating. Okay, look at this earth revolving around the sun. Look at the hands of a clock going around. Or you doing something routinely. It repeats itself. A motion which repeats itself after some time, that is called as periodic motion, right? You probably going to school every day is almost like a periodic motion, provided you should do the same things every day. Like you wake up at 7 o'clock, you brush your teeth, you have breakfast, you do your basic studies, you go to school, you come back from school and sit for studies, you refresh, have dinner, and again go back to sleep at 11 o'clock. If you do the same thing every day, I'm pretty sure nobody does the same thing every day, or else life will be very monotonous and boring, then that motion is periodic motion. But let's say one day you wake up at 7, one day you wake up at 8, one day you have breakfast, one day you don't have lunch, you don't like that sabji which is packed in your tiffin box, one day you play excessively, you don't study, then obviously that is not repeating itself, that is not a periodic motion. So whenever a motion repeats itself, it's called as a periodic motion. And what do you have associated with a periodic motion? It's basically the time period. Time period is the time after which the motion repeats itself. Now, a lot of students ask this, sir, I have a question. For example, the moon goes around the earth in around 28 days. Now, the motion repeats itself after 28 days, but think about it, after 28 into 2, okay, which is 56, or 28 into 3, or 28 into 4, even then, after 56 days also, the motion repeats itself. So why is 56 days not the time period? Have you ever thought about it? Remind me and think and let me know what you guys have to say about this in the comment section. Let me know. Even 56 days should be the time period, because after 56 days the motion of the moon repeats itself. There is a catch. The catch is the time period is defined as the smallest time after which the motion repeats itself. So 56, yes, is the time after which it repeats, but it's not the smallest time. The smallest time is 28 days. So the smallest time after which the motion actions repeat, that is called as the time period. Is that clear? Yeah. So it's not more than a cycle, I would say. So what's one cycle? One cycle is the smallest, event which can be repeated again and again. Okay. It's not because of the distance. It's not because of that. Okay. Looks like Gokulnath finally has his doubt cleared. Now there is something called as oscillatory motion. Look at these examples. This pendulum going back and forth. There is water in a tube and it's going back and forth. And look at the spring mass system, it's going up and down. Look at this ball which is sliding back and forth on this double inclined plane. These are all examples of to and fro motion, back and forth. The motion is repeating itself, yep, but it is going that side and this side, that side and this side, up and down and up, left and right. So vibrations, oscillations, they are all associated with oscillatory motion, to and fro motion, right? Like I am walking right now. I'm going here and then I'm going here. That's obviously an oscillatory motion. A lot of teachers, a lot of students have this habit. Suddenly when you are worried, you do this. You fold your hands behind and you start walking in a worried manner. So that's oscillatory motion, right? Exactly. What's the difference between oscillatory and periodic motion? Hi Prabhas. By the way, let me tell you, we are going to find the time period for this, this and this. Yep, all the time periods we will be able to calculate once we learn the equations. I'll give you a beautiful way to remember this, the difference between periodic, oscillatory, etc. And also today's chapter. Imagine a Venn diagram. Everybody knows what's a Venn diagram? Put up a yo in the chat box. Venn diagram gives you an idea of who belongs where, and it gives you the idea of sets, right? So imagine a set of motion. All the things inside it is motion. Projectile motion, 1D motion, 2D motion, oscillatory motion. So many kinds of motion are possible. So I have one subset which is periodic motion, like the earth going around the sun, moon going around the earth. Alright, so many examples, hands of a clock. Similarly, I have something called as the oscillatory motion, and these two things are quite different. Very, very important. A lot of people think oscillatory and periodic are the same thing. That's completely wrong. I'll give you an example. Right now I'm here. I go here in 1 second. I come back here in 1 second. I go here again in 1 second and I come back here in 1 second. I keep doing that. Is my motion periodic? Yes. Is my motion oscillatory? Yes. So it will lie in this intersection. It will lie in this intersection. Agreed? Because it is repeating after a fixed time interval and I'm going to and fro. But look at this. I take 1 second to go here. I take 1 second to come back. Next time I take 2 seconds. Again I take 2 seconds to come back. Next time I take 3 seconds to go here. And then again I take 3 seconds to come back. Now again I go back here in 1 second. I come back here in 1 second. Now I take 3 seconds to go here. What kind of motion do you think it is? What kind of motion do you think it is? Now I'm taking 3 seconds. Now I'll take 4 seconds. Is it periodic? No, it's not periodic. But is it oscillatory? Yes. So that's the difference. I hope you get it. Yes, it is oscillatory, but it is not periodic. Perfectly. Why is it not periodic? Because I'm not repeating the same thing after the same fixed time. Once I'm taking 1 second, once I'm taking 2 seconds, once I'm taking 3, once again I'm taking 1, again I'm taking 4. It's not repeating itself. So it is non-periodic, but it is oscillating. Yep. So in oscillation, yes, the time interval may not be fixed, may not. If it is fixed, then it's a good thing, great. So you can have things over here as well. In that intersection of periodic and oscillatory motion, you have a tiny mini subset, and that's a very special oscillation which is also periodic, but it also follows certain special properties, and that is called as simple harmonic motion. In fact, to mention properly, okay, all these periodic functions which are oscillatory, I can just write their intersection as just harmonic oscillations. Harmonic oscillations, that's the intersection, that's the name of the intersection. It's harmonic oscillations. They are periodic and oscillatory. A special subset of that one is called as simple harmonic oscillation or simple harmonic motion, whatever you want to call it. This is what we are going to study in detail, and there are some conditions for it to be simple harmonic motion. That's what is there. Is that clear? Yep, exactly, Suchi Mama. Understood? Many people know this. Okay, now you know what we are studying in this chapter. We are studying basically this part. We are not studying this, we are not studying that, we are not studying the red part, we are studying the black part or the small subset over there, which is SHM. Interesting, right? So now many people are relieved. Thank God, sir. I thought we are going to study this, we are going to study this, we are going to study this, we are going to study this. It will be such a big chapter. No, the chapter is that. Okay. Now there is one very interesting thing. So harmonic oscillation means the motion which is periodic in nature and it is to and fro. That's what it means, Arun. Periodic and it goes to and fro. So periodic oscillations, they are called a harmonic oscillation. Harmonic is just another word for periodic. So anything that repeats itself is called as harmony. It's in harmony, it's harmonic. Okay, great. Now let me show you a chart, and let me also give you a very interesting result. Imagine that there is a particle, and let's say it has some x coordinate. Okay, this is a particle of mass m, and this x coordinate is some function. It's some function of time. I am interested to know what would this function look like if the motion is periodic in nature. Like for example, the particle goes here, comes like this, then goes here, then comes like this, stops, and then say it comes here. Again it goes like this, comes back like this, again goes here, comes here, and then again stops and comes over here, and again goes like this. So if it keeps on repeating this motion, I want to know what will this function look like. Is there a general form of this function? And I'll tell you, yes, there is. So for that, I'm just going to show you a simple graph, and I'm using Desmos out here. So let's start by writing certain things like x is equal to 2, let's say sine, and I need to start with y. So y is equal to, let's say for example, sine of x, and we all know sine x function, it's a bumpy road. It starts from 0, it goes till 1, goes to 0, goes to -1, and again comes back over here. So it repeats itself, right? So is this periodic? Obviously yes. Is this oscillatory? Yes. So if on the y-axis that was position and on the horizontal axis that was time, then the position of that particle, x is increasing as time increases, and then x decreases as time decreases, and again it increases. So you can see the particle will go up and down, it will oscillate, the coordinate will oscillate, as time progresses. Okay, you can see the x coordinate increases, decreases, increases, decreases. So it is definitely oscillatory and periodic motion. What if I change this a little bit? Okay, so I'll just probably do something. Maybe I add some number like 2. Whoa, the moment I make it 2, you saw that it got expanded. Beautiful, interesting. Okay, how about I add something to it? Maybe let's say sine of 2x to it. Interesting. The moment I added sine of 2x, you can see the shape has become very weird, but still it is repeating itself. I can change the constants out here. So if I don't want this 2 here, maybe I want a number 3 over here. Oh, now it looks very different. Let's say I want a number 3 over here. Okay, then see how it looks. Wow, very interesting. Let's say I add some more numbers, like maybe 2 sine, okay, 4x. Whoa, look at that. Look at that. Oops, wait a minute. Okay, let me just put those brackets. Very interesting, so that it is very clear. Whoa, it looks like somebody's heartbeat. It looks like somebody's heartbeat. Zoop, zoop. I don't know whether you are able to see this. Are you able to see this, my warriors? Let me know. Yeah, so you can see it is a very nice, it's a very nice periodic motion. Now I can have many more such terms. Okay, maybe I can make this as 0.4 or something, and then maybe I can add some more terms. Maybe, I don't know, maybe plus 5 sine of 8x or 9x, I don't know, 9x maybe. Okay, you can see that. Whoa, look at that. That is also repeating. I don't know whether you are able to see it, but it is actually repeating itself. It's repeating itself. So essentially, if I keep on adding sine terms over here, this is something x, something constant is there, and if I keep on adding terms, the motion might become complicated, but still it remains periodic in nature. Do you see that? Oops, Bhala is saying somebody is dead. Oops, no. All right. So a lot of bloodshed happening out here. Let's get this bloodshed out. So we just saw that by adding some sine terms and all of that, you got a periodic function. So that's exactly what I wanted to tell you. So any periodic function where x is some function of time, that function can be represented. You can represent it as the sum of some sine terms, but there is no harm in using cosine terms also. So even if you use cos terms, you will still get the answer, but tan is not allowed because tan is a discontinuous function. You will learn more about it in maths. So in general, x can be the sum of sines or cosines, something like this. I can use some constant a1, I can put sine omega 1t plus phi, and then I can have something a2 sine, then omega 2t plus phi 2, and so on and so forth. I know you are wondering, sir, what is this a1, what is this omega 1, what is this phi 1 and phi 2 and all of that. Hold on, I'm going to tell you what these terms are, but for now they are some constants. So a, omega and phi are basically some constants. They are some constants. You can see that whenever you have multiple sine terms, the graph of such a function is repeating itself. It's repeating itself, hence it's a periodic function. Everybody agrees to this? Okay, yep, they will be real constants. They are all constants. Now, that means you give me any shape, basically there will be some equation describing that shape. But remember, our chapter name is something else. Our chapter name is not periodic function. Our chapter name is actually simple harmonic motion. So we'll come to simple harmonic motion, but for now, I just want you to realize that the function which is periodic is a sum of sines or cosine, where a, omega and phi are some constants. You can see the summation symbol is there out here. Harmonic and periodic mean the same thing. Remo, okay? Harmonic and periodic mean the same thing. All right, fair enough? Cool. Let's go to SHM, but before that, let's solve some questions. The motion of the hour hand of a clock is periodic but not oscillatory, oscillatory but not periodic, periodic and oscillatory, neither periodic nor oscillatory. Yep, come on, let's see how many of you can get it. So how can x be equal to both sine or, no, I did not say and, I said or, KSK. Okay, either you use all sine terms or you use all cosine terms, because you know sine and cosine, the behavior of the graph is almost the same. That's the reason for that. Okay, chalo. Most of you are saying C, Cholan, Dakshin, Gautam, Strasti, Gokulnath. All right, Thunder, rotational, yes, but out of these 4 options, Okay, looks like many of you are correct. Oh, sorry, wrong. Periodic, but not oscillating. I don't know why you said C. Why is it C? I don't know why you said C. It is not oscillating. I don't know. You guys have some special clocks or what? Where the time goes forward and after 1 hour, again it is going back. Again, the time goes forward 1 hour and again it goes back. So you are basically stuck in time. How can time oscillate? Time always goes forward. I don't know. Do you have special clocks? Please tell me. I would be very interested to buy those clocks, and it will be fun to get stuck in a loop. Oh my god, that's crazy. So it's periodic, it's not oscillatory. Next question coming up on your screen. Which of the following graphs does not represent periodic motion? Some of these graphs may be more than one correct. Yep. So looks like nobody has that special clock. Vignesh, thank you Vacha so much, and that's my whole intention to help you all. Come on. So out of these, maybe one, maybe two, maybe all, maybe three, I don't know, do not represent periodic motion. Which of them do you think it is? More than one is correct. Advanced type question. Okay, A, B, C, D. Look at the graphs closely. Observe them. Most of you are having B as an option. Some of you have A as an option. I can see that. Some of you just saying D. Some of you saying ABD. Interesting. Looks like you're a fan of ABD Villiers. All right. So, see, this is obviously out of question. This is not at all periodic. I mean, look, just look at this. I mean, do something, do some other nonsense, do some other more nonsense, then you do something else, then you do something else. It's like completely random motion. It's definitely not periodic motion for sure. Okay. C, it's heartbeat. Yes, it is a periodic motion. You can see the same thing, just it's like a rubber stamp. You take this, paste it here, copy it, paste it here, copy it, paste it here. So obviously it's repeating, so it's periodic. D, yes, whatever is there here till this point, you can see is getting repeated. From here to here, repeated. So D is also periodic, C is also periodic, B not periodic. A lot of students thought A was periodic, but let me tell you, in A, the time period is not constant. This motion is oscillatory, but it is not periodic. It's oscillatory, but it is not periodic because here time period is more, here it's less, here it's even less. Remember, the time period must be fixed. Only then it is periodic function. So hence the correct answers are A and B only. So does not represent periodic motion. These are non-periodic. This is also non-periodic. This is periodic. This is periodic. That's how it is. Yep. Is that clear? Nilkamal, nobody knows, bacha. If anybody has told you that there will be 2 attempts, I don't know how that person got to know, but there is no information as such now, but you can just guess, okay, with a pinch of salt, okay. Everybody can just guess. Nobody for sure knows what's going to happen. Okay, next question coming up on your screen. Which of the following functions of time represent periodic and which of the following functions do not represent periodic motion? So this is mathematical question. The previous one was graphical. That was slightly easy. Now we have made it slightly more difficult. More than one options could be correct. More than one options could be correct. Sam, no, I won't be. Okay, because I need to be on YouTube. Okay, every teacher will have to do different things. So I do not have so much of time to manage everywhere. All right. So simple harmonic motion will oscillate, Kela Kirti. It is, I think I just mentioned that, Venn diagram, if you are there at the start of the class, I have given you that Venn diagram. It is a combination of oscillation and periodic motion. Okay. So what about this? Sine omega t plus 4. What about this? What about this? What about this? What about this? I think I just gave you a simple way of knowing whether it is periodic or not. If you are there during my class just few minutes ago, any periodic function can be expressed as the sum of sines or cosine functions. Sine term, sine, cos. So just use the definition and see. Here you have a sine term, something omega t plus some constant. Yes, it is a periodic. This one, sine, cosine, sine, definitely it is periodic. This one, e raised to something, not allowed. Log of something, not allowed. Phi plus omega t, where is the sine or where is the cosine? So hence they are not periodic. Hence A and B are periodic. Non-periodic will be C, D and E. Understood? D is not. Be careful. Yep. So C, D, E are non-periodic. There should be sine terms in addition or cosine terms in addition, or sine, cos, in addition, or subtraction will also do. Okay, you don't think that, sir, if there was a minus sign, then will it not work? No, even if a minus sign is there, it will still work. Okay, because you can always take the minus sign inside, because you all know sine of minus sine theta is nothing but sine of minus theta. You can always bring that minus sign inside the sine term. Okay, so it works. Okay, great. Now that you have a fair idea of what a periodic function looks like, remember I just showed you just some time back, going back here. Okay, so we are going to study not periodic function but simple harmonic motion. So that's special thing. So coming back over here, yes. What would be the equation of simple harmonic motion? That's the next obvious thing on your mind, and let's see that. We just saw that any periodic motion would look something like this. X is equal to A sine omega 1 t plus phi 1 plus more terms over here. So there could be n number of terms. This is periodic motion, which I also called it as harmonic oscillations or harmonic motion. Now, what is simple harmonic or SHM, simple harmonic motion? Simple harmonic motion will not have so many terms. It will just have one term. So, if X is just A sine omega t plus some constant, then that is a simple harmonic motion. As simple as that. Understood? So it's very simple. You just have one term, it is simple harmonic. You have multiple terms, it becomes harmonic or just periodic. So this is a very special graph. What is the difference? Let's see that using our Desmos software. Okay, so when the equation has only one sine or cosine will also do. Okay, then it is called simple harmonic. Let us just go to the graph out here and let's just write X is equal to 2 sine, let's say 3, let's start with Y, because Y is the vertical axis. Y is equal to 2, okay, sine, okay, once again 2 sine 3x plus 0.2, let's say. Okay, so you can see this is a simple harmonic motion. Okay, this is a simple harmonic motion, the blue one. But this one, the Y is equal to, let's say, 3 sine 2x plus 0.5 plus I think that S was not supposed to be there. Okay, plus let's say 4 sine 3x plus 0.6. Now that green graph is definitely not a simple harmonic motion. I'll just hide the blue graph. You can see the green graph, it's not a smooth sine curve. You can see that very clearly. Can you see that, my warriors? Can you see that? Okay, so this green graph is not simple harmonic, it is just harmonic, but the blue graph, it is simple harmonic motion. Very good, excellent. Now, if you guys have understood till here, please put up a yo, please put up a thumbs up, please put up a heart in the chat box. Now let's talk about the different terms which are there, in a simple harmonic motion. The different terminologies. Each term has a special significance. This thing, this thing, this thing. Each term will affect the nature, the shape of the graph. How does that affect the shape of the graph? Let's start observing. First of all, let's make this 0. Okay, let's make this something. Okay, and let's just keep it over here. Now imagine, okay, let me just put over here A. Okay, let me put over here omega, and over here phi, I'll just put it as P. Okay, add sliders for all. Okay, it's a very interesting thing that is going to happen. I want you to pay close attention to this. Look at this graph. Look at this graph. Okay, something's going to happen, and let's see what happens when you change each one of them. Okay, let's do this. Cool. So what is the value of A? A is 1. What is the value of omega? Omega is 1. What is the value of that constant? It is 0. That's a pure sine wave, nothing else. That's a pure sine wave. You can see it starts from 0, it goes up and down like this. What do you think? What do you think, my warriors? Thank you for all the love and thank you for all the yo's. Will happen if I change this slider, this A. What do you think if I change this? If I increase this, what do you think might happen? Visualize it. A sine something, sine function just goes up and down. As the value of x, basically this line increases, it will just go up and down. If the outside term becomes big, what's going to happen? It's going to magnify it. It's going to elongate it. Then you will see this graph is going to stretch like this. Don't believe me? Check this out. Just check this out. I'm just going to change the value of A. Okay, just check this out. Look at this. Wow, interesting. And if I make this 4, it goes up till 4 and comes back till minus 4. 4 minus 4. If I decrease this, okay, look at this. If I make it 0.7, okay, it goes up till 0.7. Okay, it goes up till 0.7. This is 0.7. You can see that, and goes down till minus 0.7. Okay, this is basically minus 0.7. So that's what happens. So by changing this, I am changing. What am I changing? I'm changing the amplitude. Amplitude is how much do you go on this side or this side. If I keep this at 2, it goes from 2 to minus 2. So is the amplitude 2 or 4? Come on, my warriors. In this question, if this goes till 2 and goes till bottom till minus 2, is the amplitude 2 or is it 4? The answer is 2. It's not 4. Amplitude means if you draw the average line, or if you consider the mean line, mean and average mean the same thing. If you draw the average line, then from that point, how much does it go on either side? This side it goes to, this side it goes to. So that is basically called as the amplitude, the extent of the displacements, the extent of this side or that side. For example, I'll give you a live example. Okay, I'm standing here. I start moving like this. I go 2 meters here, come back 2 meters. I go here 2 meters, I come back 2 meters. To this side, to this side, to this side, to this side. So 2 is my amplitude. Great. Very good. Understood. Looks like perfecto. Now let's bring it back to normal. Let's say I bring it back to 1. Okay, so this is your normal pure sine graph. It goes till 1, comes back till minus 1. What do you think? Like wave amplitude, exactly same thing which you would have studied about waves back in 9th or 10th grade. It's the same amplitude, the extent of rise and fall. Correcto. Now, what do you think will happen if you change this omega term? The moment you change this omega term, what's going to happen? You're multiplying omega with x. So, if you multiply it with a larger number, then what happens is, you will see that the variations will be faster, because whatever values you are going to get, for example, when x was, pi radians, when x was pi radians, the value of sine was 0. But the moment you multiply x with some value which is more than 1, then you will reach that same point earlier. So you will see the graph will condense. Don't believe me? Check this out. I increase this. You will see if I make it 2 times, see what happens. I have reached this point at pi by 2. It has condensed 2 times. If I make this 0.5, okay, let's keep it exactly at 0.5 and see what happens. I come to this point at 2 pi, twice that. So decreasing this omega expands the graph, and increasing the omega condenses the graph. That frequency of the oscillation changes. Exactly. It's basically like frequency. Okay. I would not use the word wavelength because this is not a wave as such. We are referring to, this is actually position, this is time. So how frequently it is going up and down. So actually the horizontal axis is time, beware of that. That's why we are calling it frequency. Okay, not wavelength. So beautiful. So omega changes the frequency. Last thing, so let's get this back to 1. Okay, let's just get this back to 1. Now, if you look at the graph and see what should happen when you change this P. If you change this P, then you are adding or basically subtracting something from this inside term. So here is what happens. Right now, this P, which is phi, is 0. The moment, okay, look at this. This term is at 0, 0. I'm just going to increase this. The moment I increase this, look at this, the graph is going behind. Do you see that the graph is going behind? And if I decrease it, then the graph goes ahead. Do you see that? What a perfect thing. What a perfect thing. So increasing the value of phi shifts the graph behind, and decreasing the value of phi shifts the graph forward. So now let's try to analyze this. Imagine I choose this value to be 2. Imagine I choose this value to be, I don't know, maybe 3. Okay, and let's say I put this value over here, I don't know, something. Okay, I'll just put it over here. Now if or maybe I'll just decrease it like this. Okay, 0.7. Okay, now if these are the parameters, what it means is, okay, let's expand this. Look at this. The maximum value is 0.7 and the least value is minus 0.7. So what is the amplitude? The amplitude is 0.7. Number 1. Number 2, this omega is 3. Omega is 3 means it is now thrice as fast as a regular sine graph. It's thrice as fast. Okay, usually the sine graph would go up and down like this. Now because you have increased the value of omega, it has become more condensed. It is becoming faster. The frequency has become thrice as fast. Okay, so that's what it means when omega is 3. Okay, now just because, let me just leave it at 3. Just because this P is 1.5, you will notice one interesting thing. Look at this graph. Okay, at 0. Okay, it's little difficult. Okay, do you see this is 0? When the value of time is 0, see where the graph is? The graph is already at some point. If I make this P as, let's say, I don't know, 0.8 or something, you will see when the horizontal value is 0, the vertical point has already some value. It already has some value. And only when I make this phase 0, will I see that when my time axis is 0, my vertical point also is at 0. So this graph shifts. That means if I shift this, or if I change the value of P, you will notice that at time is equal to 0, because horizontal is time, the value of x is different. What does it mean? It just means when t is 0, time is 0 means you just started observing it. Originally, where was it? Was it at x equals to 0.4? Was it at x equals to 0? Was it at x equal to 0.2? That's what it tells me. Yes, that's all it tells me. Is that understood now? It basically shifts. The moment it shifts, it just tells me where did it start from? When you started seeing it, was x already there or not there? That's all. Okay, so let's start looking at these terms one by one. First, the equation I just told you, amplitude. Look at this. This is a point mass. It's going back and forth like this. This point over here, which is the average, that is also called as the mean position. Okay, some of you do not know this, but still I need to mention this. Okay, so this is mean position. This is extreme position. This is also extreme position. Mean is exactly midpoint of the two extreme. Extreme means the extrememost points, the last points after which the motion does not even exist. It's between these 2 points. If this is x equals to 0, this will be x equals to minus a, that will be x equals to plus a. That is amplitude, that is also amplitude. Makes sense, right? Okay, so that is what mean and extremes are, that is what amplitude is. So amplitude is the extent of the displacement from the mean position on the either side. Yep. Now mean is basically the average. It's mean means average, that's all. Okay. Next, frequency. I just told you about frequency. Frequency is how quickly that particle goes back and forth. We already had defined something called as the time period. So if t is nothing but the time period of oscillation, then the frequency of oscillation will be 1 by t. And what's the unit of frequency? It is basically hertz. Just to give you a numerical example, just imagine the time period of certain oscillation is 0.2 seconds. It takes just 0.2 seconds to complete one round. Okay, 0.2 seconds. Then the frequency will be 1 by 0.2, which is nothing but 5 hertz. Meaning in 1 second it will complete 5 oscillations. 0.2 seconds, 0.2 seconds, 0.2 seconds, 0.2 seconds. So 5 times. So 5 oscillations in 1 second. So hertz is the unit of frequency. So this F stands for frequency. Frequency. What is frequency? It's the number of oscillations per unit time. Fair enough? Everybody clear till this point? Great. Now the last thing that you need to remember is, well, omega. Remember that omega was there? Okay, that omega was there in that term and in that big expression of simple harmonic motion. That omega is nothing but 2 pi divided by time period. Now does this ring a bell? Does this somehow ring a bell in your head? Think about it. Think about it. Does it remind you of some chapter? Does it remind you of some theory which you have already studied? Yes. Does it remind you of something? Angular velocity. Yes, Roshni says angular velocity. Correct. Yep. This was studied in circular motion. You saw angular velocity was 2 pi by time period. Somehow that same term comes over here. Why is it so? You will understand that in the third class. Okay, you're going to see the derivation for that. It's exactly resembles circular motion, but you're going to see that why that happens in third class. But for now, omega is 2 pi by t, which is also 2 pi f. This is something which you have already studied in uniform circular motion. But nevertheless, we'll see why is it so later on. But remember one thing, this is not called angular velocity here. Here it is called angular frequency. That's what it is called. It's called as angular frequency. How quickly it is covering, number of oscillations. And the unit of that is not hertz, it is a radian per second. You can see that very easily. 2 pi is radians, t is in seconds, so radians per second is the unit of omega. So be careful. So for this numerical example, if I had to find out omega will be 2 pi into f is 5, so it will be 10 pi radian per second. It will be 10 pi radian per second. Omega is the symbol, that's it. Yep. So be careful. So that's what we just figured out. Now probably it makes a little bit of sense. See, 2 pi radians is one circular motion. 2 pi radians is one complete circle. Maybe 2 pi radians resembles or correlates or is very much similar to one oscillation. 2 pi radians, I am repeating, 2 pi radians corresponds to, I am not saying it is equal to, one oscillation. Think then 10 pi radians. 10 pi radians will have how many 2 pi radians? 10 pi radians will have 5 2 pi radians. So 5 oscillations in 1 second. So that's probably something for you to get or visualize what angular frequency is. So when I say the angular frequency is 2 pi radians per second, it just means it completes one oscillation in 1 second. If I say the angular frequency is 4 pi radians per second, 4 pi is 2 times of 2 pi. So 2 oscillations in 1 second. That's all. Are you getting the feel of this omega? So omega gives you how quickly the oscillations are being covered per unit time. That's all. That's all. So omega is 2 pi f or 2 pi by t. Frequency is 1 by time period. Perfecto. Okay. Great. So that is different, Anadurai. That's don't worry about it. We'll talk about it when you study quantum physics, which is the last chapter of 12th standard, one of the last few chapters. Now, here comes the next part. The only term which is remaining, that is phi. Let's talk about it. Imagine, I tell you, x is equal to, okay, x is equal to something like a sine omega t plus phi. Okay, this is your generic equation. This is your general SHM equation. We just saw what A does. A decides the amplitude or the extent. Omega decides how quickly it is covering that. The only thing remaining is phi. I'll tell you what this phi does. Just imagine if I ask you, put the value of time as 0. When time is 0, what will this equation end up being? It will become x is equal to a sine. Remember, time is 0, it will just become sine phi. Correct? X will become a sine phi. Now just substitute certain special values of phi, you will immediately understand what it means. Remember, when time is 0, that means initial. So when time is 0, that means you have just started. This x is special x, x0. This x0 is nothing but the initial position. So let's try out some special values and see what do you get. For example, if you put the value of phi as 0, if you put the value of phi as 0, sine of phi, sine of 0 will be 0. So x0 will also be 0. Make sense, everybody? So if phi is 0, x0 will also be 0. Perfect. Next, let's try to use phi as pi by 2 radians, which is 90 degrees. Sine of 90, 1. So x0 will be a. So x0 will be basically a. Make sense? Next, let's put phi value as pi. Let's put phi value as pi. So if I put the value of phi as pi radian, then the value of x0 will be, come on my warriors, sine of pi, sine of 180 is 0. So x0 will be 0 again. If I put the value of phi as 270 degrees, which is 3 pi by 2. So if I put phi is equal to 3 pi by 2, then the value of x0 that I will get, sine of 270 is minus 1. So I'm just going to get this as minus a. Now look at this, look at this, look at this, and look at this. What does it tell you? If somebody gives you the phase constant as 0, that means that initially the particle is located at the origin going towards this side. It's going towards this side. If somebody tells you in this expression the value of phi is 90 degree or pi by 2 radian, that means initial position. Remember, x0 was initial position. It is already here. In that oscillation, when you just opened your eyes, you already saw the particle was here. Okay, it's already here. If somebody tells you the value of phi is pi radian, that means the particle is at 0 but going this side. It's going this side. And if somebody tells you the value of phi is 270 degrees or 3 pi by 2 radian, that means the particle has already reached that side, and that's when you opened your eyes and you saw it over there. Exactly. So the value of phi tells you when you close your eyes and then suddenly open it, where exactly the particle is. Where is it? So do you get a sense out of it? Think about it. 2 pi radians is one oscillation, and one circle is having 4 different quadrants, and you can see a simple harmonic motion also has 4 parts in it. Which are the 4 parts? From here to here, from mean to extreme, part 1. From extreme to mean, part 2. From this to this, part 3. From this back to this, part 4. So if I tell you the value of phi, is 60 degrees, where do you think the particle is? Where do you think the particle is? Come on, my warriors, think. 60 degrees is between 0 and 90. So that means the particle is somewhere here and going that side. So when you just open your eyes, you see the particle going this side. That's what you're going to observe. If somebody tells you the value of phi is 150 degrees, 150 is second quadrant, it's less than 180 but more than 90. So that means that particle or that block has reached the extreme and it is somewhere in between going towards this side. It's going somewhere this side, it's between 2 and 3. If somebody tells you the value of phi is 200 degrees, it means the particle went there, came back and it is here but not yet reached here and it is going this side. That's all it means. And if somebody else tells you that the value of phi is 300 degrees, then it means it has crossed this position and it is here and it is going towards that side. That's all it means. So what does phi tell you? Phi tells you the initial position. So the first one was x is equal to a sine omega t. The second one was x is equal to a sine omega t plus pi by 2. Third one was x is equal to a sine omega t plus pi. The next one was plus 3 pi by 2. So in general, it tells you where is it initially. Yeah. I will start it, Hanadurai, after some time. I mean, after fluids. Okay. We have a lot of things to cover. So the phase, what is this called? The value of phi. It's called in physics, in simple harmonic motion, it is called as the phase constant. The phase of any oscillating or vibrating particle at any instant gives you where is it at that point when you just open your eyes, or basically when time is equal to 0. Okay, so that's what it is. Fair enough. Let's move to two simple equations and then we'll solve lots and lots of questions. Are you ready? Are you all pumped up? Okay. Is it interesting? Yeah, too many equations, but let me tell you, you will love this chapter once you start solving the questions. Yep, it's going to be very amazing. Yes, definitely, Vaishal. The channel name is JEE Enthuse. So definitely we are meant for you guys to crack JEE, KVPY, JEE Advanced, JEE Mains, everything. I'm very good. I'm very good. Okay. Alright, let's do this. If I tell you, I know x is equal to a sine omega t plus phi, this is nothing but position of that simple harmonic motion. How will the velocity look like? Everybody knows from the first chapter, 1D kinematics, velocity is the derivative of position. So we all know velocity is nothing but dx by dt. So if I am talking about dx by dt, it means derivative of, this a is a constant, so I can just bring it outside, derivative of sine omega t plus phi. So what is the derivative of sine omega t plus phi? Let's see. Come on, what is the derivative of sine? Derivative of sine is cosine. Derivative of sine is cosine. Do not forget that. So strictly speaking, this will be cosine omega t plus phi. But there is one catch. Let me tell you. See, derivative of sine of x is cos of x. But derivative of sine of ax plus b. We have done these kind of questions, but let me just give it to you as a formula now. If you want, you can watch my derivatives class where I have done all these things. The derivative of this guy is not just cos of ax plus b, but it is a times. This a also comes outside. Yes, that constant which is getting multiplied by x also comes outside. So that's something which you need to be aware of. So omega will come over here. So this velocity will be nothing but a omega cos omega t. That's very, very important. Now, here is the thing. Come on, my warriors. What is the max and the minimum value of a cosine function? What is the max value of cos? If you put anything inside cos, what is the maximum value you can get for cos? 1, right? And what is the least value you can get? Cos of 0 is 1, you can see. Anything else you put, it will never be more than 1. And the least value is -1. Correct. So what do you think is the max value of velocity and what do you think is the least value of velocity? The max value will be plus a omega when cos is 1 and least value will be minus a omega. But if you think about it magnitude wise, acha, by the way, what is this minus sign telling you? Minus sign tells you the direction. This is left side, this is right side. Now try to visualize this. Try to visualize this. When the particle goes back and forth, okay, when the particle goes back and forth, see, this particle will stop here as well as here. The particle will actually stop here and here. So the least possible speed is 0. Speed wise, the minimum speed is 0 because speed can't be negative. Speed always has to be positive. But velocity wise, you can see, once when it reaches here, it goes with maximum speed there, plus a omega. So while going here, it has plus a omega. It goes there, stops, comes back. Here it comes with minus a omega. So the maximum speed is when it reaches the center and the maximum speed comes out to be plus a omega. So this is the max speed of that particle. Very, very important. Is that clear? Yes. So minus a omega just represents the direction, but speed wise it is still a omega only. So the modulus of this is still a omega. So this is the maximum speed. So where does the particle have maximum speed? The particle has maximum speed at the central, mean, average position. What is the maximum speed? The maximum speed is a omega. Where does it have minimum speed or least speed? It is at the two extreme positions when it just stops and turns around. How much is it? It is 0. Fair enough? Understood this concept? Okay, understood this concept? Perfecto. Let's write down this thing again over here. So x is a sine omega t plus phi. Then velocity came out to be a omega cos omega t plus phi. And we just saw that this is nothing but the max speed. Perfect. Now, here is what we are going to do. This velocity, let me write it down in a very peculiar way. I'll write it down like this, a omega. Remember, sine square plus cos square is 1. Using this identity, since sine square plus cos square theta is equal to 1, so 1 minus sine square is basically cos square. So therefore, root of 1 minus sine square is basically cos. Using this trigonometrical identity, what do I get? Here, instead of cos, I can write it as 1 minus sine square omega t plus phi. Correct? 1 minus sine square omega t plus phi. Now, what is sine square omega t plus phi? Look at this expression. Can you look at this expression? You will get it immediately. So, a omega root of 1 minus sine square is x by a. So, it will be x square by a square. Now, take the LCM. You will see it will become a omega root of a square minus x square. The whole thing divided by a square, but that is again inside the root. So, it will just become a. This a and this a will cancel. You will get this as omega root a square minus x square. So this is value of velocity. When will you need it and why will you need it? See, this expression is also very important, but here you got velocity. Here you got velocity as a function of time. You can see time term over here. Here you get velocity as a function of x. That is the difference. That is the difference. That's all. Okay. So sometimes time is given, you need to find speed. Sometimes position is given, you need to find speed. That's the major difference in these two expressions. You should know the derivation. You should know the final formulas. Okay. I put this up for all of you right over here. Velocity is, you know, a omega cos omega t. It is also omega under root a square minus x square, a square minus y square, whichever variable you want to use. So yes, KSK Kritika, if you use x is equal to a cos omega t plus phase constant, then your velocity will become minus a omega sine omega t plus phi. But don't worry, the final outcome will not change. In fact, when we have a problem solving session, I will teach you how you can change from sine to cos or from cos to sine, and it really does not matter at the end of the day. Okay, so anyways, in the question the equation will be given to you. Next term, acceleration. So acceleration is nothing but derivative of velocity. But I think I know what is velocity. I just know what is velocity. Velocity, I just figured it out. It was a omega cos omega t plus phi, right? So how about substituting that over here, and let's see what do we get. We'll have derivative. Remember that a will just come outside, correct? That a will just come outside, and we'll have omega and cos of omega, even this omega will come outside, a and omega, cos of omega t plus phi, because those are constants. What is the derivative of cos? What is the derivative of cos? The derivative of cos is minus sine. Derivative of cos is minus sine omega t plus phi, and for the same reasons like I explained you before, when it is derivative of cos x, it is minus sine x. But derivative of cos of ax plus b, then it is minus sine ax plus b, and that a also comes outside. So you should have this omega outside. Omega into omega is omega square, so it will become minus a omega square sine of omega t plus phi. So that is nothing but your acceleration. What is it? That is your acceleration. You have to remember this. Yeah. So acceleration is minus a omega square. Velocity was a omega cos. In fact, if you notice, if x is sine, velocity is cos, and acceleration is back to minus sine. Derivative of sine is cos, derivative of cos is minus sine. The term which is outside changes. For x it is a, for velocity it is a omega, for acceleration it is a omega square. That minus sign will automatically come over here. That's it. Is that clear? Is that clear? Very good. Now think, what will be the max value of acceleration? What will be the max value of acceleration? Come on, the max value of sine. The max value of sine is obviously plus 1. So the max value of acceleration will be a omega square. Understand that. Okay, don't worry about that minus sign. The minus sign just gives you the direction. It just gives you the direction. It is not going to give you the magnitude. Okay, so the magnitude wise, the max acceleration is a omega square. Now after I know this, I can play around with this. I'll tell you how. See, I just got, since x is a sine omega t plus phi, I got velocity is a omega cos omega t plus phi. We got acceleration is minus a omega square sine omega t plus phi. So if you notice, here there are some interesting terms. I'll tell you how. Observe this expression carefully. I'll tell you what you should observe for. Minus, bring it here, and then put also omega square here, and just in the brackets just put a sine omega t plus phi. What is this a sine omega t plus phi? It's nothing but x. So this will be just nothing but minus omega square x. So this is another important equation. So what I've just done is rearrange this, manipulated with this equation. I brought omega square here, a and sine omega t here. I know that is x, so I just got it as minus omega square x. What does this tell me? This just tells me, if you want to use this equation, then use it when it is a function of time. Use this when you want it as a function of x. So as a function of x or as a function of time, you decide. Now is it understood? Okay? So these are all the formulas that we have just studied right now, and it's all going to be there in the PDF. Don't worry about it. Yeah. So minus omega square x, and acceleration is minus omega square a sine omega t. Great. Okay. Cool. Now, if you have got it till here, how will the graphs look like? How will the graphs look like? The graphs are going to be very simple. I'll tell you why. For example, if I put the value of phi as 0, and look at the graph for x, if it is a sine omega t, the value for velocity will be a omega cos omega t. Value for acceleration will be minus a omega square sine omega t. If you just draw the graphs quickly, think in your head, how does a sine graph look like? A sine graph will start like this, it will go 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 like this. The maximum height will be plus a, the least height will be minus a. That's position graph. Okay, so this will be position graph. How will the velocity graph look like? It's a cosine graph. Cos graphs always start from plus 1. So it will start from here, it will go like this, 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 and oops, I think I made a mistake. Yeah, it will go like this and it will come here. Yep, that's it. So it starts from plus a omega and the least value will be minus a omega. That's what the velocity graph will look like. How will the acceleration graph look like? How will the acceleration graph look like? Think about it. The acceleration graph is a negative sine graph. It's a negative sine graph. So if it is a negative sine graph, what will happen? Sine graph is like this. The negative sine graph will be like this. Oops, sorry, wait a minute. I should make use of proper, yep. So it will go like this, like this, like this, and like this. So this is how the acceleration graph will look like. So if you know one thing, you'll get to know the other thing. That's all. Okay, and I think I have drawn more wavelength over here. My bad. I should have drawn this graph like this. Okay, probably now it is fine. Okay, I think now it is fine. Okay. All of them should have the same wavelength. Yes. Okay, so if I started from here, 0, 90 degrees it is 1, 180 it is 0, 270 it is minus 1, and back to 360. So that's what it is. And this is basically one time period. This is one time period. Yep. Yep. Fair enough. Got it? Yeah. So this is how the position, velocity, and acceleration. Look at the interesting things. When position is 0, velocity is maximum. That means when you are at the mean position, center, velocity is maximum, acceleration is 0. When amplitude or when you reach the extreme end, velocity is 0 because you have just stopped. But acceleration is maximum. You can see that acceleration is maximum. Again, when you come back, position is 0, velocity is negatively maximum, acceleration is 0. When you go to the other side, the negative side, you stop over there, velocity is 0. That time also the acceleration is maximum. So velocity and acceleration are not maximum at the same time, they are maximum and minimum at different times. That's something which you need to remember. Good enough. Great. So that's what I have put it over here for your reference. Let's start with some questions. Okay, so the maximum displacement of an oscillating particle is this much. If its time period is 3.14 seconds, what is the velocity at the mean position? What is the acceleration at the extreme position? Let's start doing this question. First of all, what's given to us? Let's start writing it down. We know that the time period, okay, the time period is 3.14, that means pi seconds, and the maximum displacement, that means the amplitude, is basically 0.1 meter. This is what we know. From the time period, we can find out many things like omega. Omega is 2 pi by the time period, so it is 2 pi by pi, which is basically 2 radians per second. So that's the value of omega. Now what is asked? What is the velocity at the mean position? Guys, think velocity at mean, that means basically x equals to 0, is maximum. It is maximum. And how much is it? It is a into omega, right? Do you remember it? And what is a? I think I know it. It is 0.1. And what is omega? It is 2. So it will be basically 0.2 meters per second. So that's the velocity. Great. Next, what is the acceleration at the extreme position? Okay, acceleration at extreme position, you can use this equation minus omega square x. So minus omega is 2, so 2 square. Okay, and x, extreme is basically the amplitude, which is 0.1. So I'm just going to get it as minus 0.4 meters per second square. But if I'm asked the magnitude of it, then it will be just 0.4 meters per second square. So 0.4 meters per second square and 0.2. So option A is correct. Very good, Vinay Cholan. Very good. Very good. Excellent. So that's the correct answer. Perfecto. Moving on to the next question coming up on your screen. Here it is. The displacement of a particle is given by this expression. I want you to be familiar with this expression. Something sine something time plus something. This is amplitude, this is omega, this is phi. In seconds, okay. The initial displacement and the maximum velocity of the particle are how much? Okay. Now if you look at this expression, clearly the 20 is nothing but the amplitude. The 6 is nothing but omega. Phi is nothing but pi by 6. Just compare it, visualize it. A sine omega t plus phi. That's all. Now, the next thing. What is the initial displacement? The meaning of initial displacement means when time is equal to 0. So just substitute the value of time is equal to 0. So y will be equal to 20 sine, put the value of time as 0 plus pi by 6. So 20 into sine of 30. Sine of 30 is half. So it is going to be 10 meters. So that is your initial displacement, 10 meters. Maximum velocity. What is the formula for maximum velocity? I just told you maximum velocity is a omega. So what is a? A is 20. What is omega? Omega is 6. So it will become 120 meters per second. That's your next answer. So 120 and 10, that means option D is correct. Is that, oh no, why are you saying C? It is not C, bachalo. It is option D. Got it? It's not B also. Be careful. 120 is here, but 10 root 3 is wrong. Sine of 30 is half. Be careful. Okay, so the answer is D. Many of you made a mistake. Vinay, you can leave a comment after the session ends. I'll definitely help you out. Okay, just leave a comment. Okay, next question. There is a particle which is performing simple harmonic motion. The equation of its motion is so and so, where x is its displacement and the displacement of the particle is 3 units. Then how much is its velocity? Okay, let's again write down what and all we know about this question. So comparing this with our original SHM equation, the amplitude is 5, the value of omega is 4, and the value of phi is basically minus pi by 6. What is the question? If the displacement is 3, if x is equal to 3, the question is how much is the velocity? How do you do this? Well, one might think, sir, I know what to do. I'll use x is equal to a sine omega t plus phi, and then I know x, I know a, I know omega, I know phi. So from this I'll find time. Then I'll use velocity is a omega cos omega t plus phi. I know phi, I know omega, t whichever I find over here I'll put it here. I know a, I know omega, I'll find out v. That's a very lengthy process, but you can avoid that lengthy process. How? Observe. I just know one formula, v is omega root a square minus x square. Yeah, haven't you learned this formula? And let's see, what do we do now? What is omega? Omega is 4. What is amplitude? It is 5 and x is 3. Interesting. 5 square is 25. 25 minus 9. 25 minus 9 is nothing but 16. Root of 16 4. 4 4s are 16. So hence the answer is 16 meters per second, which is option D. Thank you, Soham. Thank you so much. Welcome, Ram Prasad. I hope you are enjoying, and if you are joining a little bit late, make sure you start watching this right from the beginning after the session ends. Alright, so 16 meters per second, that's the answer. Moving on to the next one. Perfecto. Pranesh, we don't know that yet because it's not even started. Frequency of a particle is 24 Hertz. Amplitude is 4 centimeters. Initial displacement is 2 centimeters towards negative side. Write the equation for displacement. Only one of them is correct. Let's try to figure out how to solve this. I know for sure when you started looking at the theory, you were like, my god, this is going to be one hell of a maths. But when you start looking at the problems, you're like, yes, If you know the equations, if you know the formulas, and if you understand it, that's it. It's just plain substitution and you'll get the answers fatafat. Okay, so we know the frequency over here. So the frequency is 24 hertz. The amplitude is 4 centimeters. And the displacement, that means initial displacement, is 2 centimeters on the negative side. That means minus 2 centimeters. It's given on the negative side. Okay, now once I know frequency, I can also find omega. Remember, omega is 2 pi f, so it will be 2 pi into 24, which is 48 pi radian per second. So omega done. Remember, what is our original expression for SHM? X is a sine omega t plus phi. Out of these, amplitude I know, omega I just found out. Only thing unknown is phi. How do I find out phi? Make use of this information. Initial position is minus 2. Substitute it. Let's see what do we get. If I substitute x is equal to minus 2, amplitude as 4, sine of, remember this was initial, this stands for initial. So that time value will be 0 plus phi. So 4 comes below, minus 2 by 4 is minus half, is equal to sine of phi. Everybody fine till here? Everybody fine till here? Okay. So I've just substituted time as 0 in the SHM equation. Phi I don't know, amplitude I know, position is minus 2 as per the given question. Now think, whose sign is minus half? Obviously, the value of phi, you can look at it over here, the phi value will be minus 30 degrees, which is minus pi by 6 radian. So we got phi also, so that is also done. So now check which of the following options works. But remember, this amplitude was 4 centimeters. So technically this is 0.04 meters. So 0.04, 48 pi t minus pi by 6. Is it option B, guys? Yep. Perfecto. Perfecto, Roshni Cholan. Very good, Chandan Arun. Perfect. So that's how you get it. Moving on to the next question. Let's move on. Okay. So what do we have? The maximum speed of a particle is given and the maximum acceleration is also given. Then the angular, actually this should not be velocity, my bad, it should be frequency. The angular frequency, because omega, although the symbol is same, here we refer it as angular frequency. How much is it? Okay, let's try to analyze. Maximum velocity is 2 meters per second. V max is 2 meters per second. Maximum acceleration is 4 meters per second. A max is 4 meters per second square. Do I know some formula for velocity, maximum and acceleration? Let's think. So how about this? You leave a comment after the session ends, I'll definitely help you out with it. I think I know. The maximum velocity is nothing but given by A into omega. Correct? A into omega is the maximum velocity. So that is equal to 2. Similarly think, what is the formula for maximum acceleration? In case you have forgotten, let me remind you. Say velocity used to be A omega cos omega t. So this used to be your maximum velocity. Acceleration used to be minus A omega square sine something. This used to be your maximum acceleration. So maximum acceleration is A omega square. Now what do? Divide this with this. So A omega square divided by A omega will be 4 by 2. A goes, omega goes, so omega will be 4 by 2, which is 2 radian per second. That's exactly what you wanted, which is option D. So if you just know the formulas, you just have to play with it. You just have to play with it, that's all. Yes, Suchi Mama, very good, Chandan. Perfecto, perfecto. Yes, BN gamers, you are quite late. Okay, moving on to the next one. Interesting. Let's see. What do we have? There is a particle which starts simple harmonic motion from the mean position. Its amplitude is A, time period is T. At the time when the speed is half of the maximum speed, the displacement is how much? At the time when the speed is half of the maximum speed. Okay. First of all, what is the max speed? The max speed is a omega. We all know that. So half of V max is basically a omega by 2. Cool. So when the speed is half of the maximum, that means the velocity is a omega by 2, how much is the displacement? That means the displacement is asked. How do I find this out? I think there is no question of getting time unnecessarily. Let's not involve time because it will unnecessarily complicate the situation. Maybe this expression will help. Velocity is omega root a square minus x square. I just gave you this formula when I told you about velocity. How about this? Achha, the velocity is a omega by 2. Velocity is a omega by 2, right? It is given in the question. Velocity is half the maximum speed. Omega, I don't know. Amplitude is a, okay, minus x square. Oh, omega is not given, but I don't bother because omega just get cancelled. So how about squaring? So square both sides and see what you get. A square by 4 is equal to a square minus x square. Take x square here. Take this a square by 4 there. Okay, so it will look something like this. Now a square minus a square by 4, that's 3a square by 4. Now that's x square. So how much will x be equal to? It will be a root of 3, root of 4 is 2. So a root 3 by 2, do I have it somewhere? Yes, I have it over here. Option C. Thank you, Muskan. Yep. So 1 minus 1 by 4 is 3 by 4. So that root of 3 will come over here and root 3 by 2. Perfect. Perfect. Yes, option C is correct. I hope that is correct option. Yes, it is. Perfect, right? So you are getting the hang of simple harmonic motion. It's all about equations. Let's do one last question. Let's do one last question. Now let me tell you, I had planned something more also, but unfortunately I won't be able to do it today. So here is what I'm going to do. I'm going to shift that small part which I was planning to do today in the next class. Don't worry. I'm not going to hurry up. And that's what I think you love about this nurture series and me and my teaching style, that I don't hurry up things. I want to make sure you understand it. That's what my whole aim is. So the how many lectures? I have planned around 6 to 7 classes. Promise me you're going to attend all of them. Okay, it's not going to be like, sir, please do it in one shot, please take a marathon session, please complete it in 7 hours. Your head will freeze, brain will freeze. Don't do that. The xt graph of a particle undergoing SHM is given by this graph. What is the acceleration at time is equal to 4 by 3 seconds. Let's solve this question. Okay, so what do we have? What do we have? A graph which goes like this. Clearly from this graph, since it's position versus time, think about it. Think about it. I got to know how much is the amplitude. How much is the amplitude? Quickly let me know in the chat box. Very true, Suchi Mama. Very nicely said. At nurture, you have been nurtured. How much is the amplitude? How much is the extent? It is 1 centimeter. Perfect. This is time axis. What is the time period? Come on, quickly answer this question. What is the time period? What's the time period? Think about it carefully. What's the time period? Come on, think. What is the time period? Is it 4, 8, 12 or something else? One oscillation is covered in 8 seconds. Perfecto. Everybody got it? Great. Last thing, find the acceleration at this much time. Okay, I'll tell you what. Use this expression. Acceleration's formula is minus a omega square sine omega t. This is the formula. What about phi? Well, since it starts from 0, it clearly means the value of phi is also 0. If the graph starts from 0, the value of phi is also 0. Makes sense? So this is the expression of the acceleration. So substituting the values, what do I get? Acceleration is minus amplitude. Amplitude is 1. Everything is in centimeters, so I will leave it as centimeters, don't convert into meters. Omega square. Oh, I don't know omega. So from this, omega will be 2 pi by t, which is 2 pi by 8, which is pi by 4. So omega is basically pi by 4 radian per second. I've got the value of omega. So let's put it over here. Pi by 4 whole square into sine omega is nothing but pi by 4. Time, it's given, it's 4 by 3. So this is going to be minus pi square by 16 into sine of 4 cancels, sine of pi by 3. Pi by 3 radians is 60 degrees. Sine of 60. How much is sine of 60? Come on, my warriors. Sine 60 is root 3 by 2. So hence it will become minus pi square root 3. 16 to the 32. That will be everything in centimeters square per second. And I think we have it somewhere over here. Is it option D? Check this out. Wow. Did you guys understand this question? Yep. Yep, Cholan, don't worry. I'm going to do it. Next 2-3 minutes. What a brilliant session. What a brilliant session. Okay. Now, yeah, that's the answer. I'm going to give you a homework question. So, by the way, the answers for that will be posted in the Telegram channel. This part I'll be doing it in the next class. So ignore this. Okay. So I'm just going to skip through these slides. Okay. Quickly. This is your homework. This is your homework. Post the answers in the comment section. You can solve this question just based on whatever I have taught you today. And I'll be showing you who all have solved this homework in the next class, right at the beginning or somewhere in the middle. And do not forget to check out our courses on the Pro subscription right at your fingertips, including my courses. And the best part is you get to learn in English as well. And there are plenty of micro courses, including the KVPY course is available at a very good discounted rate when you use my coupon code SHHPRO. And in fact, all the links are right now there in the description box if you're watching the video. So if you're watching the video, do not forget to check it out. Right over here, there is KVPY course. Most of you would have completed your internal exams and you want to prepare for the next 1 month. Remember, the KVPY date is 9th of January. It's all there over here. You can just go, click, you can change whichever course you want to. For example, KVPY crash course. That's it. It's there. It's there for 1,800 rupees. My coupon code automatically gets applied. Okay. So I hope you have all enjoyed today's session. And do not forget to recommend this channel to all your friends and your classmates who would love to enjoy these kind of classes. And yes, thank you for smashing that like button and thank you for subscribing to Enthuse. This was Shreyas here, your physics master teacher. Next time, I'm going to do, spring mass systems, oscillations and energy in SHM. All of this with me tomorrow at 7:30 p.m. sharp. Take care and have a great time. Hasta la vista.